Hi everyone, this is Professor Moser. I just wanted to go over the final exam review sheet with everybody. These types of problems are kind of a selection of the assortment of the types of things that you might see on the final exam. So anything that's related to the final, any type of question that appears on the final, there will be a example of one here in the study guide. So let's kind of go through this together to give everybody a head start on your studying. The first batch of questions have us solving some different types of equations. And in the first one, we want to solve 8x divided by x plus 1 equals 4 minus 8 divided by x plus 1. This is what we called a rational equation. The first thing we want to do, if you recall, is look for our restrictions. In a rational equation, remember, we can't ever have a value of the variable that will make the denominator equal to 0. So here we have one type of denominator. It's x plus 1 equals 0. If we subtract 1 from both sides, we would get the value x equals to negative 1. So that means that for us, x cannot be negative 1, as that is going to be a restricted value. If you were to plug negative 1 into this equation, it would result in a division by 0. Okay. So we now know that. Now we're ready to go ahead and solve this thing. The procedure for solving rational equations is we want to multiply both sides of the equation by the LCM of all of our denominators. Here, the only denominators we have are of the form x plus 1, so that means that the LCM is x plus 1. So what we're going to do is we're going to eliminate the fractions by multiplying both sides of the equation by the LCM. That is equivalent to multiplying every single term of the equation by x plus 1. Like this. For the first multiplication, if it helps, if you're thinking of working with it in terms of a fraction, you can always put that x plus 1 over 1, but these will cancel due to fraction multiplication, and we're going to be left with 8x over 1, which is just 8x. On the right-hand side, this is going to be a distribution. 4 times the quantity x plus 1 will give us 4x plus 4. And then with the second fraction, again, if it helps for fraction multiplication, put it on top of 1. Our x plus 1's cancel, and we're going to be left with 8 times 1, which is 8. And don't forget we had a negative sign out in front, so that ends up being a negative 8. So far, so good. We've successfully eliminated all of the fractions. And what we have now is just a basic linear equation. We can combine terms on the right-hand side. Positive 4 minus 8 is negative 4. The next step would be to bring all of our x's to one side. So I'm going to go ahead, I'm going to subtract 4x from both sides. This will give us 4x equals to negative 4. Divide both sides by 4, and we get the proposed solution x equals negative 1. Okay. So we work it out, we solve the problem effectively, but notice that what we came up with was a value that was on our restricted list. Okay. We know that x cannot be equal to negative 1, which means that this particular value was an extraneous solution. So even though negative 1 came out as the proposed solution, we realize that it isn't going to work at all. So the question then becomes, what is the solution set to this problem? The answer is, well, we had one value of x. However, that value of x didn't work. Therefore, there are no solutions. Okay? So you can either write the empty set, or you can literally spell out no solution. Okay? So this is a good review of solving a rational equation. The key is you have to do one of two things at the beginning. Either you should form your list of restrictions, which is formed by setting all of the denominators equal to 0. Solving for those values that make the denominators equal will give you undefined values if you plug them in. Those are our restricted values. X will not be able to be equal to any restricted value. From there, you find the LCM, multiply every single term in the equation by the LCM. That clears fractions, like what we had here. And then once your fractions are cleared, you can go ahead and solve it like you're used to. If you don't find the restrictions in the beginning, that's okay. what you would have to do is make sure that at the end of the problem that you would to take your solution and plug it back in and check it. In my opinion, it's much easier to work out the restricted values first than what it is to have to go and plug a value back in and check it at the end of the problem. Let's take a look at question number 2. In question number 2, we want to solve the equation square root of 3x plus 18 equals to x. This is a radical equation. The steps would be to isolate the radical by itself, which we do have this time. We have the square root all by itself on the left-hand side of the equation. The next step would be to then go ahead and raise both sides of the equation to the second power. We know that on the left-hand side, the square root and the square cancel because those are inverse operations. That leaves us with 3x plus 18. And on the right-hand side, we now have x squared. Our radical is gone. What results now is a quadratic because of the x squared term. To solve this, we want to get one side to be 0. So I'm going to subtract 3x and subtract 18 from both sides. This will give us 0 equals x squared minus 3x minus 18. To solve this, we're now going to go ahead, we're going to try to factor this. So we're going to go ahead and factor this. This will factor as x minus, maybe I spoke too soon, x minus 6 times x plus 3. There it is. Again, if you're unsure of your factoring, you can always distribute this out and check it. But this will factor out to x minus 6 times x plus 3. We now set each factor equal to 0 individually, like this. For the first one, we add 6 to both sides. We get the solution x equals to 6. For the other equation, we subtract 3 from both sides, and we get x equals to negative 3. One of the things that we talked about when it comes to radical equations that have even indexed roots, things like a square root, a fourth root, a sixth root, etc., these are solutions you have to check. Okay? For example, I'm going to check just one of the two for everybody. Let's check x equals to negative 3. When I check that as a solution, that means I have to plug it into the original. Says this 3 times negative 3 plus 18. Will that equal to negative 3? That's going to be the square root of negative 9 plus 18. That's the square root of 9. But the square root of 9 is positive 3, and that does not equal to negative 3. So as it turns out, this solution right here, x equals to negative 3, that one ends up being extraneous. So that's an extraneous solution. And honestly, you didn't have to check this. You didn't really need to go all the way down to realize this. At the very first point, when you plug negative 3 into that equation, when you realize that you have a square root equal to a negative, we know that that can't happen. So you could have even stopped here and realized that that particular value of x is going to be extraneous. I'll leave it up to everybody else to check the other one, but I guarantee if you plug x equals to 6 into this equation, you will get a true statement. So we get one solution on this one, x equals to 6. This is another great example of a type of equation where you have to be careful when it comes to radical equations, especially radical equations with even indexes like square roots. You have to check your solutions on those. Let's take a look at the next example, question 3. Here we now move on to polynomial equations, namely quadratics. We have 2x squared minus 6x plus 1 equals to 0. To solve a quadratic equation, or for that matter, to solve any polynomial equation, the first step would be to get one side equal to 0, which is already done for us. The next step would be to try to factor the left-hand side if you're able to. Okay. 2x squared minus 6x plus 1 will not factor nicely. It's not possible to find nice integers whose products of 2 and 1 will work to give us -6. So if you find yourself trying to solve a quadratic equation, and if you're unable to factor it, then you want to use the quadratic formula. Okay, this is a formula you absolutely have to know for the final. Okay? The quadratic formula is this. So if you have a quadratic equation in standard form, namely of the form ax squared plus bx plus c equals to 0, a is the coefficient of x squared, b is the coefficient of x, and c is the constant term, then the quadratic formula says that the solution to this equation is going to be the following expression. It's x equals -b plus or minus the square root of b squared minus 4 times a times c, all divided by 2 times a. Because our quadratic is already in standard form, we see that the value for a is 2, the value for b is -6, and the value for c is +1. So let's go ahead and plug those into the quadratic formula. It's the negative of b, which is the opposite of b, so it's the opposite of -6, plus or minus the square root of b squared minus 4 times a times c, and this is going to be all divided by 2 times a, and a also happens to be 2. From here, we just want to be very careful, follow nice and neatly the order of operations to simplify this. On the outside, the opposite of -6 we know is +6. Plus or minus, we have the square root of -6 squared, that's a +36. For this product, the way that I often like to think of it is I think of this sign as going with this number. So I think of this as like the product -4 times 2 times 1. That's going to be -8 times 1, which is -8, all divided by 2 times 2, which is 4. We can simplify the inside part now. 36 minus 8 is going to give us 28 over 4. And we can simplify it yet a little bit more, because even though 28 is not a perfect square, it is divisible by the perfect square 4. 4 goes into 28 7 times. And what's nice about that is we can simplify the square root of 4 to 2. We can do one more thing. If you look at all of our coefficients in this expression are divisible by 2. So you can factor out a 2 from each of those, and that will leave us with 3 plus or minus the square root of 7, all divided by 2, and those are our 2 solutions. Okay. You can leave it with the plus minus notation if you want to split it apart to see them individually. One solution is 3 minus the square root of 7 divided by 2. The other solution is x equals 3 plus the square root of 7 divided by 2. So that's our first example with a having to use the quadratic formula. Again, the quadratic formula, as long as it's in standard form, it's x equals -b plus or minus the square root of b squared minus 4ac, all divided by 2a. Let's take a look at the next one. In question 4, we want to solve another quadratic. This is going to be 3x squared minus 2x plus 4 equals to 0. Again, you should try to see if you can factor this. And I believe this one will factor as a 3x and a x, a 2 and a 2, and then we're going to need a minus and a plus. Let's see if that works. That'll give us a 3x squared minus 6x, nope, plus 2x, nope, so that doesn't work. So you can try to keep factoring this thing. You may or may not be able to find the factorization, but again, let's not worry about it. Let's go right to the quadratic formula. A is 3 b is -2, and c is equal to +4. So again, from our quadratic formula, the solution is going to be -b -b plus or minus the square root of b squared minus 4 times a times c, all divided by 2 times a. We get x equals, the opposite of -2 is +2, plus or minus the square root of -2 squared is 4. -4 times 3 is -12. And then -12 times 4 is a -48. All divided by 6. This is x equals 2 plus or minus the square root of -44, all divided by 6. And now we can definitely simplify this. First thing we notice is that we have a square root of a negative. So we can put that negative into the square root outside of that number. That will leave us with the square root of 44 all over 6. And recall that I, by definition, is the square root of -1. And we don't need to use it for this question, but I is designed such that it has the property, if you square it, I squared equals to -1. So we get x equals 2 plus or minus I square root of 44 over 6. We can reduce this, however. 44 is not a perfect square, but it is divisible by the perfect square 4. 4 goes into 44 11 times, like this. And then simplifying this, we get 2 plus or minus 2i squared of 11 over 6. And then as we saw before, each of these coefficients, the 2's and the 6, are divisible by 2. So we can reduce this to 1 plus or minus I squared of 11 over 3, simply by dividing each of those coefficients by 2. So we get two solutions. They happen to be complex conjugates this time. One solution is 1 minus I squared of 11 over 3, and the other solution is 1 plus I squared of 11 over 3. Again, it's up to you how you want to represent your solutions. I'm fine either way. You can write it using the plus minus notation. If you want to separate it out into two different values, you can do that as well. So that was our information on solving styles of equations. The next thing we come to is arithmetic with complex numbers. They ask us to take 5 minus 2i and square it, and to simplify this. Okay. Remember, at the end of the day, if you're doing arithmetic with complex numbers, it doesn't matter whether you're adding, subtracting, multiplying, or dividing it. At the end of the day, you want your number to be written as a complex number, which should be of the form a plus bi. So it should be such that you can very easily look at what is the real part of the complex number and identify what is the complex part of the complex number. In order to do this exponent, remember what an exponent means. This means to take the complex number 5 minus 2i, and we're going to multiply it by itself. And because that's a binomial, it has two terms, we need to use that general distributive property, or some of you might refer to it as foiling. We have 5 times 5, which is 25. 5 times -2i is -10i. -2i times 5 is a -10i. And then a -2i times a -2i would give us a positive 4i squared. We can combine the middle terms. This is going to be 25 minus 20i plus 4i squared. And now notice, in the standard form of a complex number, there shouldn't be anywhere where you have a power of I squared. We know that I squared is equal to -1. So everywhere you see an I squared, let's replace it with the value -1, like this. So this ends up being 25 minus 20i minus 4, and now we can combine those like terms. 25 minus 4 is 21 minus 20i, and now that's our final answer. So it's of the form a plus bi. Anybody can very easily look at it and see that the value for a is 21, and the value for b, the complex part, is negative 20. Something that's a little bit more subtle is division with complex numbers. Let's take a look at this. In example 6, we have 3 divided by the complex number 4 plus I. And again, our goal is the same. You can think of this as division of complex numbers. The real value 3 inherently is thought of as being the complex number 3 plus 0i. It just has no imaginary part to it. But the goal is the same. We want to divide this and write our answer of the form a plus bi. In class this semester, we talked about this, but the procedure for dividing complex numbers is to multiply the top and bottom of this fraction by the conjugate of the denominator. If you have the expression 4 plus I, its conjugate is going to be 4 minus I. It's the same two terms, but with the sign in between them switched. Okay. So in general, if you have the complex number a plus bi, its conjugate would be of the form a minus bi. You're just changing the sign of the complex part of the complex number. So let's go ahead and do this. We know that this is allowable because we're just multiplying by a form of 1. 4i minus 1 over 4i minus 1 is 1. But this will allow us to do the division. In the numerator, when we multiply it out, we're going to have 3 times 4, which is 12. We're going to have 3 times negative I, which is a negative 3i. In the denominator, we have 4 plus I times 4 minus I. You can do this multiplication really one of two ways. One way is just to kind of do it like we did with the last problem, just distribute. 4 times 4 is 16. 4 times negative I is negative 4i. I times 4 is 4i. And then I times negative I is a negative I squared. The other way you can do this multiplication in the denominator is if you notice that anytime you multiply conjugates together, right? This is kind of like the reverse factorization of a difference of squares. We recall from basic algebra that if you take a plus b times a minus b, that's equal to a squared minus b squared. So you could do the same thing here. If you had 4 plus I times 4 minus I, that would have been equivalent to 4 squared minus I squared. Let's see that here in a second. The numerator stays the same. We have 12 minus 3i divided by, in the denominator, these middle terms cancel. The negative 4i and the positive 4i cancel. So notice we do get 16 minus I squared. We know that I squared is equal to negative 1, so we can plug that in there. This is going to be 12 minus 3i divided by 16 minus a negative 1 is the same thing as 16 plus a positive 1, which is 17. And so now we're ready to write our final answer. We've completed our objective, but again, we want to make it look like it's in the form a plus bi. So let's put it in the form a plus bi. To do that, all I'm going to do is split apart the numerator. I can write it as 12/17 minus 3/17 I, and that is our final answer. Let's take a look at question 7. We're asked to solve an inequality. So this is a linear inequality. The key to solving these is you solve them almost as if you would a general equation, but to remember that it has the special property that if you ever multiply or divide both sides by a negative, that will require us to switch the sign of the inequality. So I'm going to distribute a negative 4 first. This is negative 4x minus 8 is greater than or equal to 3x plus 34. I now want to bring all of my x's to one side, and maybe I'll just go ahead and I'll subtract 3x, since I think a lot of students prefer to have the variable on the left-hand side of the expression. So we get something that looks like this. The x's over here cancel. I'm left with negative 7x minus 8 is greater than or equal to 34. All of our x's are now on the left-hand side of the inequality, so we want to isolate them. Let's go ahead and add 8 to both sides. We get that negative 7x is greater than or equal to 42. And now we're ready for our last step. To get the x by itself, we need to divide both sides by negative 7. But keep in mind, that's that division by a negative. That's going to take this symbol, and it's going to reverse the direction. So we end up getting x is less than or equal to 42 divided by negative 7 is negative 6. So the solution to the inequality is x less than or equal to negative 6. With inequalities, though, this is just one way in which we have to represent our solution set. So on the exam, you'll be asked to do all three types of solution. The first one is the solved inequality, which we've done. We also want to graph this thing. So let me go ahead and do that. We have a number line. Somewhere on the number line is the number negative 6. If it says x is less than, we know that less than means go to the left. So I'm shading everything to the left of negative 6. And then furthermore, because of the type of inequality, less than or equal to, that means we can be equal to negative 6. So that point will be included, so it gets a filled in circle. The last way we can represent our solution set is with interval notation. Again, I find it for students, if you do the graph first, it makes it much easier to write it down in interval notation. If we look at the shaded region from our graph, it goes all the way to the left towards negative infinity. It goes as far to the right as negative 6, which is included, so that gives it a bracket. Okay. So this is our solution to question 7, both as a solved inequality, graphed interval, and the solution set in interval notation. Let's take a look at number 8. In question number 8, we're asked to solve the inequality. The absolute value of 2x plus 5 is less than 7. And you have to be a little bit careful here. So on the review, I only put one of our two types of absolute value inequalities. If you remember from class, there's two different types here. Okay. So the types depend upon the direction in which the inequality faces. If you have an inequality of the type, let's say, the absolute value is less than some positive number. Okay, let me just call it C for a minute. Then the solution to this type of inequality is going to be negative C less than or equal to U less than or equal to positive C. I believe in the notes we refer to this as an inequality of type 1. However, and there's not an example of this in the review, but just be aware, if the inequality goes in the opposite direction, if you're looking at the absolute value of U is greater than or equal to C, and again, I'm just assuming C is positive right now, then this is going to be a disjoint inequality. The solutions to this type of absolute value equation are going to be the following. It's going to be U greater than or equal to C, or U less than or equal to negative C. Okay? So just be aware, we had two different types of absolute value inequalities, and the setup to solve them is different from each other. Here, this would be an absolute value equation of type 1. So the setup is going to be, we're going to take the thing on the inside. We set it strictly less than the number we have, but then you also have to set it greater than the negative of that number, like this. This produces a compound inequality, which contains 3 pieces. And the moral of the story is whatever you do to one piece, you have to do to all 3 pieces. So to isolate x, we would first need to subtract 5. That's going to give us negative 12 is less than 2x is less than 2. And then the next step would be to divide everything by 2. Because we're still working with inequalities, remember, if you had to end up multiplying or dividing by a negative in this situation, then not only would you have to switch the direction of one inequality, you would have to switch the direction of all inequalities. So that same rule would hold true. If you're working with a compound inequality and you multiply every single term by a negative or divide every single term by a negative, make sure you switch the directions for all of your symbols. Okay? Here we did not have to do that, but we end up with the solution negative 6 is less than x is less than 1. We can now show our solution set in graphical notation. Negative 6 is somewhere on the number line here. 1 would be to its right. If you see how the x is sandwiched in between, so we shade the region in between those two values. And then because it's a strict inequality, neither of those two would be included in the solution set. If I write the shaded region in interval notation, this is from negative 6 not included up to positive 1, which is again not included. So we get a solution set that looks like this. Let's go ahead and take a look at the next question. In question number 9, we want to solve an absolute value equation. The absolute value of 5x minus 3 is equal to 12. If you recall from the notes, let's suppose we have a value c greater than 0, then the solutions to the equation, the absolute value equal to c, are either u equals to c or u equals to the negative of c. So if I want to solve the absolute value of 5x minus 3 equals to 12, the first step would be to isolate and get the absolute value by itself. That part is already done for us. We have absolute value on the left-hand side, a number on the right-hand side. So the next thing we're going to do is let's go ahead and set this equal to 12. And we also need to set it equal to negative 12. So we get two equations we have to solve. For the first one, we're going to add 3 to both sides. We would get 5x equals to 15. Divide by 5, divide by 5. We would get x equals to 3 is one solution. Over here, we would add 3 to both sides. We would get 5x equals to negative 9. Divide both sides by 5, and we get x equals negative 9/5. Okay. So question number 9, absolute value. We have two solutions, positive 3 and negative 9/5. Let's take a look at the next one, question number 10. Here we want to solve the absolute value of 3x minus 4 plus 6 equals to 1. So for this equation, notice that we don't have the absolute value term by itself. So our very first step would be to try to isolate that absolute value. So I'm going to subtract 6 from both sides. That would give us the absolute value of 3x minus 4 is equal to negative 5. From here, what I see a lot of students will do is just like what we did with the last problem. You set 3x minus 4 equal to negative 5, or you set 3x minus 4 equal to the opposite of negative 5. Okay. However, that's not going to work. You can do this, you can work it out, and you can solve and get two values of x. However, both of those values would end up being extraneous. And the reason why is right here. Before we go any farther, take a look and inspect what you have. This statement right here is saying that the absolute value of some expression is equal to a negative number. Well, that's impossible. We know that absolute value is the minimum 0 or a positive value. So it doesn't matter what value of x you have here, there's no value of x you could ever plug in that would end up resulting in this absolute value producing a negative number. So just by noticing that, you can stop right there and say that there's going to be no solution. Okay, no solution. In the heat of the moment, if you don't pick up on this or if you don't catch this, You could continue on and come up with two solutions, but both of them would be extraneous, and you would only ever be able to see it at that point if you plugged it back in and checked it into the original equation. So with absolute value equations, again, you have to be a little bit careful here. If at any point in time, if you end up with an expression, the absolute value equals something that's negative, stop right there and say no solution. If you're less careful, then just go back through and check your solutions each time. The next question we come to is now a graphical based question. Question number 11 asks us to list the x and y intercepts. So on this graph, the x-intercept is any point where the graph crosses the x-axis. That would be right here. This is the ordered pair -3, 0. So that's our x-intercept. And our y-intercept is wherever the graph crosses the y-axis. That's going to be down here. That is the ordered pair 0, -9. So again, where you cross the x-axis, that's your x-intercept. Wherever a graph crosses the y-axis, right here, that is the y-intercept. Again, those are points on the graph, so please make sure you're writing them as ordered pairs, x, y. X comes before y in the alphabet. In the ordered pairs, same thing too. The x-coordinate comes first, then followed by the y-coordinate. The next thing we want to find is the domain and the range. The domain goes with the x values. The range goes with the y values. So if I'm trying to find the domain, what I'm looking for is I'm looking on the x-axis. I want to ask the question, how far to the left to how far to the right does the graph go? The leftmost point on the graph, notice, is this one right here. And it has an x value which would have been equal to -4, but notice because of the presence of the open circle, that point is not included. The point that goes the furthest to the right is this point here, which is filled in, which is 0 for x, and so that will be included. And if we notice how the curve appears anywhere in between those two, this is going to produce our domain set. The domain of this function is going to be from -4, which is not included, to 0, which is included. Let's now go ahead and find the range. To find the range, now we're looking on the y-axis. And again, it's an ordered set, so you want to go from smallest to largest, which on a vertical line would be from lowest to highest. The lowest point on the graph is right here. The highest point is right here, which is not obtained because of the open circle. And if you notice, we get every y value or every height in between those two. So the range set is going to be, it goes as far down as a minimum of -9, which is included, and it goes up to a maximum of, looks like what, is that 7? Yes, 7, which would not be included. Another important skill set within this question is find the value of f of -2. If you recall that back in the old days, we used to call the ordered pairs x, y. Whenever we start to work with functions, we can also envision the pairs as being of the form x, f of -x. So if we want to find f of -2, we need to look at the graph and see where's x equal to -2 at. That would be right here. And then locate the point on the graph. The point on the graph looks to be right here, and that has a y value equal to -5. So because the point -2, -5 is on the graph, again, that's the same thing as -2, f of -2. That means that f of -2 is equal to -5. Question 12 is another graph-based question. For the symmetry on this one, if you look at this curve in number 12, notice that if I draw the y-axis, that's technically the line x equals to 0, it would cut the curve into two identical pieces. So we would say that this graph has a y-axis symmetry. That also means functionally that this would be an even function. So one of the things that we talked about in the class is that if you have a graph with y-axis symmetry, that happens if and only if you have an even function. The other kind of symmetry, which is not being shown right now, is we also had an origin symmetry, which would be a graph that looks something like this. So think about like the cube root of x or x cubed, something like that. Those would be graphs that would exhibit origin symmetry. To identify an origin symmetry, any point that's connected to the origin via a straight line, that same line continued on the other side of the origin would intersect a point on the curve that is the same distance from the origin as the original point. Okay, so that's what we mean by an origin symmetry. We also discussed how in class you can also view it as a double reflection. If you take your graph and reflect it about the vertical axis and then reflect that graph about the horizontal axis, or the other way around, if it returns the original graph, then that also indicates an origin symmetry as well. Okay. Find the domain and range. Well, if we just very quickly look at this graph, on the x-axis it goes as far to the left as -3, which is included, and to the right to +3, like this. On the range, the lowest point is a y value of -2, and it goes up to a point, 2 points actually, that have a y value of 0. So domain -3, 3 included. The range is from -2 to 0. Again, those are both included as well. The value of the function at 3, f of 3, here's the point when x equals to 3. This has a y coordinate of 0. So f of 3 equals to 0. For the next part, we're trying to solve where is f of x equal to -2. So this is kind of a reverse lookup. This height here corresponds to all y values that are -2. And we see that that point occurs precisely when the value of x on the x-axis is 0. So when is f of x equal to -2? Well, that happens precisely when x equals to 0. That point also happens to be a local minimum or a relative minimum, which is right here. So it has a minimum of 0, and the value of the minimum is the y coordinate, the function value, which is -2. We are now asked about which intervals the function is decreasing and increasing. Remember, these are intervals in the domain, so you're looking at the behavior of the function and the corresponding x values for which it's doing that behavior. As we read from left to right, notice that the graph is initially moving downward, so it's decreasing from x equals -3 until we hit x equals to 0. Okay. So it's decreasing between this x value and this x value. Also, quick note for intervals of increase, decrease, and constant, those intervals are always given using parentheses, by the way. So if you talk about increase, decrease, or constant, you should never be using brackets. Those will always be open parentheses. Now, what happens after x equals to 0? If we continue to read the graph from left to right, notice that now the graph is moving in the upwards direction, which means that the graph is now increasing. And the graph increases from x equals to 0 until we hit x equals to 3 when it stops. So that's going to be from 0 to 3 is where the function would be increasing. Let's take a look at question number 13. This is the information that's regarded to lines. So if we consider the line 2x minus 3y equals to 6, they ask us to find the slope and the y-intercept. Easiest way to do that is to put it in slope-intercept form. We want it to look like y equals mx plus b. So it's just a fancy way of solving this equation for y. I can subtract 2x from both sides. These cancel. We get -3y equals a -2x with a +6. The next step to get y by itself is to divide every single term by -3. And we get y equals -2 divided by -3 is equivalent to a +2/3 x, and then 6 divided by -3 would give us -2. So this line, put in slope-intercept form, looks like 2/3 x minus 2. The slope is the m value. That's the coefficient of x, which is 2/3. And the y-intercept would be this value here, which would be the order pair 0, comma, -2. If we want to graph this curve, so it's y equals 2/3 x minus 2. We know m is 2/3. We know that the y-intercept is -2. So to graph a line like this in this form, you simply begin by plotting the y-intercept, which is -2, and then you use that slope as rise over run to find an additional point on the graph. If I run 3, meaning go 3 to the right, 1, 2, 3, I have to rise 2. That gives me another point on the graph, and then you can simply connect the 2 points to make your line. Remember, the line is infinite. It should go in both directions, so I'm going to have the arrows here. Questions 14 and 15, I'm going to skip them. Those are part of the review material for the class. Okay, those weren't necessarily points of emphasis for us. But again, from back in either Math 101 or a previous class, you all should know how to find the equation of a line as well as perpendicular and parallel relationships. Okay. The next thing we come to is writing the standard equation of a circle. The standard equation of a circle is of the form x minus h squared plus y minus k squared equals to the radius squared. And this is when the circle has as its center h comma k, and the radius is going to be r. So if they give us the center and they give us the radius, all we have to do is plug it into our standard form. It's going to be x minus the x coordinate of the center, which is -2 squared, plus y minus the y coordinate of the center squared, and this is equal to the radius squared, which we're going to write as 5 squared. For the standard form of the equation, the only thing I would want you to do to simplify this is to simplify any double negatives like this. X minus a minus 2 is the same thing as x plus 2. So we can write this as x plus 2 squared plus y minus 4 squared. If you want to do 5 squared and write 25, you can. I personally find it's helpful to leave it as 5 squared because then visually it's just easier to see what the center is going to be. To me, what the radius is going to be. In question 17, this time they give us the reverse problem. Now we have the equation, and we want to find the center and the radius. So the center is going to be located at -1, 3. Remember, in the standard form, it's a value that sits behind a negative sign here. So if it helps, just look at what's in the parentheses with your x and take the opposite sign of that. The opposite of +1 is -1. The opposite of a -3 would be a +3. So this would be the center of your circle. And now be very careful. We also want to find the radius. The radius has to be something here that's being squared to get the number 5. Well, what would we have to square to get 5? Well, the answer would be its square root. So this is going to be a radius of square root of 5 units. So just pay close attention to this. The number that you see on the right-hand side isn't the radius of the circle. It's what's being squared to give the number on the right-hand side, is it? So for example, if you had something that's equal to 16, we know that 16 is 4 squared, and that circle would have a center of a radius of 4. If you have something like this, if it's equal to 7, then the easiest way to rewrite that number as a square is you can rewrite it as the square of its square root, right? And now you can see that a circle that had this part would have a radius of square root of 7 units. In the next batch of questions, we now move on to our functional material. In particular, in question 18, we're asked to find the domain of a function. we have f of x equals 5 divided by 2x squared plus 5x minus 3. This is a rational function, okay? To find the domain of a rational function is to find all of the values x such that you can plug them into the function and you get a real output out. For us, that means we're going to focus on the restricted values, which means we want to see where is that denominator going to be equal to 0. If the denominator is equal to 0, then this expression will be undefined, and those values of x will not be in the domain of the function. So for a rational function, set the denominator equal to 0. We're going to solve this. Luckily, this factors as 2x and x, 3 and 1, and it's going to be a positive and a negative. Set each factor equal to 0 individually. Solve each one. This will give us, for instance, add 1 and divide by 2. You're going to get x equals to a half. Subtract 3 from both sides, and you're going to get x equals to negative 3. So for the domain of this function, the restricted values, we see that x cannot be equal to negative 3, and x cannot be equal to a half. You can leave it like this, but it's much better to put it in interval notation because that's the proper way to write domains. They're sets. This should be everything from negative infinity up to, but not including negative 3. Union everything from negative 3 up to a half. And I'm running out of space, but union, then everything from a half to positive infinity. So this is the domain of a rational function. That answers question number 18. Very briefly, let me talk about some of the other types of domain of functions you could have. So again, on the review sheet for the final exam, the question will be about the domain of a function. And I only gave you, for that particular example, a rational function. If you're looking for domains of some of the other types of functions we came across, for example, if you have a polynomial, polynomials are constructed by repeated additions, subtractions, multiplication, and exponents. Those things have domain all real numbers. Okay, those basic operations are always defined, so they never have any issue. So that domain would be from negative infinity to infinity. For rational functions, we just said it a moment ago, if you have a numerator over a denominator, you set the denominator equal to 0 and solve, and those would be your restricted values. Those would be the numbers that are not in your domain. If you have radical functions, so it depends. If you have an even root, like a square root, a fourth root, etc., in order to take the square root and get an even number, we require the thing on the inside of the function to be greater than or equal to 0. If you have an odd root, like a cube root, fifth root, seventh root, etc., those would have domain all real numbers. So with radical equations, there's two cases. Even roots, you need the inside to be greater than or equal to 0. And if it's an odd root, then it would be all real numbers. If you have an exponential function, a to the x, they have domain all reals. The other class of function we studied in class together was a logarithmic function. So if you had, let's say, like log base b of something, okay, the value inside of a log has to be greater than 0. So if you're solving a domain question and it involves a log function, you take the inside of the logarithm, you set it greater than 0 and solve, and that would give you your domain for logarithms. Okay. So again, we had one example in the exercises for the review, but be aware that if the question is about the concept of domain, I could give you any kind of function on the final. It could be a polynomial, rational function, a radical function, an exponential log, and we would kind of have to know how to work those out. In the next question, we come to algebra of functions. So we're given the function f of x equals x squared minus 4. And we have a function g of x, which is equal to 2x minus 3. And we're asked to find the following things. Question 19 is we want f minus g. So be careful here. Make sure you use good parentheses. This is taking the function f of x and subtracting, I'm going to put it in parentheses, the function g of x. Because when you're subtracting, if g of x has multiple terms, you need to make sure you're subtracting every single term that belongs to g. That can be done by distributing the negative sign in. This gives us negative 2x plus 3, which simplifies to x squared minus 2x minus 1. So this would be your function f minus g. For the domain of f minus g, don't look at the final result. You have to go back to the original two functions. We talked about this exclusively in class. The domain of f minus g is the domain of f intersected with the domain of g. Well, f is a polynomial. It's x squared minus 4. So it has domain all real numbers. G of x is also a polynomial. More specifically, it's a linear function. It too has domain all real numbers. And therefore, the intersection of the two will also be all real numbers. So the domain of f minus g is all real numbers. In question number 20, we want to now look at the composition. This is g open circle f of x. We call that g of f of x, which means that you want to take the function f and plug it into the function g, like this. So I focus on the outer function first. The outer function is the function g. What does g of x as a function tell us to do? Well, g of x says take 2 times your input and subtract 3. What am I plugging inside of g? Well, I'm plugging in f of x. F of x is x squared minus 4. So everywhere I had an x in the function g, I'm replacing it with the expression f of x, which is x squared minus 4. And then from here, it's just a matter of simplifying it. We get 2x squared minus 8 minus 3, which is 2x squared minus 11. So that would represent the function g composed with f of x. In question 21, we now want to do the composition but in the other direction. So let's do that. So in 21, we're now looking for f of g of x. This is f composed with g of x. So this time the outer function is, maybe I'll super color code it here. Let's get fancy. So I did f in orange last time. Let's stick with that theme. And now what I'm sticking into f is the function g of x. So I'm going to start with the outer function f. As a function, what does f tell me to do? Well, f says to take your input, square it, and then you're going to subtract 4 from it. Now, what am I plugging into f? Well, as the input for f, we're putting the function g. G is defined as 2x minus 3. So wherever I saw an x for the function f, I need to replace it with the expression 2x minus 3. So this is going to be 2x minus 3 quantity squared minus 4. And now it's just a matter of simplifying this. Be very careful. That's a binomial squared. 2x minus 3 squared means to do 2x minus 3 times 2x minus 3. If you expand this out and combine like terms, I'm going to skip this step, but you would get 4x squared minus 12x plus 9 minus 4, which ends up simplifying to 4x squared minus 12x plus 5. And this would be the expression f composed with g of x. It's important, if you take a look and if you compare and contrast the answers from 20 and 21, we see that if you change the order of composition, you get a very different answer. And that was discussed. We said that in general, function composition is not commutative. If you switch the order, you get in general a different function. Under certain circumstances, namely when two functions are inverses of each other, would you get the same result? But in general, you get two different answers when you do f composed with g of x and g composed with f of x. As a follow-up to this, in question number 22, we are asked to do f composed with g of 5. Well, from the previous answer, we already know what f composed with g of x is. It's this thing right here. So all we need to do is take that function, and we're going to evaluate it at 5. So everywhere I see an x, I can put 5. Like this. This is going to be 4 times 25 minus 12 times 5 is 60 plus 5. That's 100 minus 60 plus 5, which is 40 plus 5, which is 45. So to find f composed with g of 5, if you already know what the function f composed with g is, then you can simply plug it into that function. Another way and another approach that you could have done this that's helpful, especially if you don't have that f composed with g function handy, is to do the following. So if I want f composed with g of 5, this is f of g of 5. So you'd first take the 5 and plug it into g. The g of 5 is 2 times 5 minus 3. That's 10 minus 3, which is 7. And then that value 7 then has to go in the inside of f. So now f is going to be 7 squared minus 4, which would be 49 minus 4, which is yet another way to get that answer of 45. The next question says true or false. The collection of ordered pairs represents a function. If you remember, the definition of a function says that to each value in the domain, we have a correspondence of exactly one value in the range. So the domain set, this is our collection of x's. What should be true to be a function is that each x in your domain set has to correspond to exactly one value y in the range. In terms of ordered pairs, what this simply means is that none of the x values can be repeated. If I look at my x values that I have here, I see that the x value -2 gets repeated. In particular, this ordered pair says that -2 in the domain is being associated with +2, and this one would say that -2 is also being associated with +6. So because we have one value in the domain that's corresponding to more than one value in the range, that means that this collection of ordered pairs does not define a function. So the answer to that question would be false. In part B, it says the graph of x plus 3 squared plus y squared equals to 9 represents a function. Well, this one's a little bit more difficult to see, but if you think about what kind of equation this is, that's the equation of a circle, right? This represents some circle. If you wanted to be more specific, it has a center of -3, 0, and it would have a radius of 3. So we know the shape of what this graph represents. And if you know the graph of it, then you can apply what we call the vertical line test. The vertical line test says that as long as no vertical line intersects the graph in more than one point, then it would be a function. However, for this graph, we know that a circle, you can find many vertical lines. In particular, there exists at least a single vertical line that intersects the graph in more than one point, and so that means that this is not a function. And again, that's by our reasoning, that comes from the vertical line test. So this graph does not represent a function. That too would be false. The next two questions correspond to graphing our transformations of functions. So I'll refer everybody to the notes. But if you recall, in our class, there's certain classes of functions that we really kind of focused and highlighted on. Those are polynomials, in particular quadratics. We also know the shape of x to the n for n even and n odd, right? Your even degree polynomial like x to the fourth, x to the sixth, x to the eighth kind of look like this. If you have an odd degree polynomial like x cubed, x to the fifth, etc., their shape kind of looks like this. We also talked about the square root graph, the cube root graph, absolute value. We did exponentials, the two types of exponentials, whether the base is bigger than 1, whether the base is between 0 and 1, and the corresponding logarithmic graphs whose bases are bigger than 1 or between 0 and 1. So those basic graphs, you have to have those memorized. We call those our parent graphs. They're fundamental and you have to know their shapes. If you know the shapes of those graphs, for example, the square root of x would look like this. Using that parent function, I can now graph the function in 24 because it's just going to be a vertical shift down by 3 units. So by knowing the graph of my parent function, I can graph this one by simply shifting everything down 3, and it will have the same overall parent shape. The important point that we always want to kind of keep track of with the square root is that starting point, if you will. Normally it appears at 0, 0. If we shift it down 3 units, now it's going to appear at 0, -3, and it has the same shape as its parent function. In question 25, we now want to graph f of x equals the absolute value of x minus 1 plus 3. If you look at f of x, its main basic form is that of an absolute value function. And we know that the graph of the absolute value of x looks like a v. It's this. It's technically piecewise linear. It looks like the graph of negative x for x less than 0, and it looks like the graph of positive x for x greater than or equal to 0. The way that our function f is a transformation of the parent function is we have a vertical shift up 3 units, and we also have a horizontal shift to the right 1 unit. So I'm going to take my parent function graph, and I'm going to take every point, I'm going to move it over 1 to the right and then up 3. So the most important point as it pertains to the absolute value graph is the vertex. This graph will now have a vertex that's located at 1, positive 3. And you can move some more points over if you want, but this is going to be the graph of f of x. It's obtained from the graph of the parent function absolute value, composed with a shift of 1 unit to the right and a vertical shift of up 3 units. So this is about halfway through the final exam review. So I'm going to stop this video here, and now there'll be a second video, which will be part 2, that will cover the remainder of the final exam review.